Let's start with by going over the basics of deterministic policy gradient or DPG, and I will call it DPG. Now, this is a type of policy gradient method that's used in reinforced learning, but specifically when the action space is continuous. That's important because in continuous settings, we can't just list out every possible action and try them all. Okay, now in most traditional policy gradient algorithms, we work with a stochastic policy. That means the policy gives us a probability distribution over actions. We don't get a single answer. We get probabilities and we sample from them. But DPG works differently. It learns a deterministic policy. So instead of giving probabilities, it gives us one specific action for a given state. And why does that matter? If you are working with environments where actions are high dimensional and continuous like robotics or control tasks, sampling from distributions can be inefficient and slow. DPG skips that by learning a direct mapping from state to action. That saves us from having to integrate over the whole action space every time, which is a big plus in terms of speed and sample use. And okay, let's look at the network structure DPG uses. The core idea is pretty simple. We have got an actor critic setup. On one side, we have the deterministic actor. That's the network that gives us our policy, which we call, what was that? Mu theta of S, meaning given a state S. The actor tells us which action to take. On the other side, there is the critic network. The critic is responsible for evaluating how good a given action is in a given state. It's a Q function, so we write it as a QW of S and A, where is S is a state and A is the action. But that's not the full story. DPG also uses target networks. These are just delayed, slowly updated versions of the actor and critic. So we have a target actor which is just mu theta prime of S and a target critic QW prime of S and A. Okay. These target networks are used when computing updates to stabilize training. They don't get updated at every step, instead they track the main network slowly. And to sum it up, there are a few main pieces you need to know here. First, the deterministic policy is what gives us direct control over actions. Second, the Q function critique tells us how good those actions are. And third, the learning signal, the policy gradient, is based on the chain rule, and that's how we update the actor. And fourth, we use target networks to avoid instability. And finally, all of this is trained using experience replay, meaning we store transitions and sample from them randomly. That helps break correlation and improves learning efficiency. And that's okay. Now, theory part and deterministic policy gradient theorem. This is what makes DPG work. It gives us a way to compute a policy gradient without having to sample actions from a distribution. That's the big advantage. And normally, in stochastic methods, we would need to integrate over all possible actions, and that's expensive. But this theorem tells us that under certain assumptions, we can compute the gradient of the expected return using a deterministic policy directly. And here's how the formula looks. You can see here. This is equals to expected value of the gradient of Q with respect to A, evaluated A alpha equal mu theta S times the gradient of mu theta with respect to theta. So in words, we are taking the derivative of the Q function with respect to the action and then chaining that with how the action changes with respect to the policy parameters. That gives us a way to push the actor in a direction that improves performance based on how the critic evaluates actions. And let's see how this compares to the stochastic policy gradient. In the stochastic case, the policy gradient looks different, and there we have, you can see. So we are using the log probability of the policy multiplied by the Q value. The issue is that these often has high variance. Because we are sampling from a probability distribution, we get noisy gradients. On the other hand, the deterministic version avoids this by working with one fixed action. The result is lower variance and usually more stable learning, especially when action spaces are large. And I hope that's okay. Let's stop here. Now that we understand what DPG does and how its networks are set up, we'll walk through the algorithm itself step by step. So the process starts with initialization. We create the main networks, the actor, which we call mu theta, and the critic QW. These both start with random weights. Then we create the target networks, which are just copies of the actor and critic. The target actor is mu theta prime, and the target critic is QW prime. These target networks help smooth out the updates and keep rings stable. We also set up a replay buffer. That's where we will store our experience tuples, states, actions, rewards, and next states. And once everything is set up, we enter the main training loop. For each episode, we first reset the environment and get the initial state. And because the policy is deterministic, we need to introduce noise during training to make sure the agent explores the space. Otherwise, it might just get stuck in the same pattern. So we add some random noise to the action. And then at each step, the agent selects an action by passing the current state through the actor, adds noise for exploration, takes the action in the environment, and stores the result, the transition, into the buffer. After collecting some transitions, we sample a mini batch from the buffer. That means we randomly pick a set of stored transitions to train on instead of relying only on the latest one. This helps break the correlation between consecutive experiences and makes training more stable. And updating part is here. How we update the critic. Now, for each transition in the batch, we calculate a target Q value. That's done by taking the reward plus the discounted value of the next state using the target networks. Then we compute the loss for the critic, which is just the squared error between this target and the Q value predicted by the critic network. The goal here is to make the critic better at predicting how good a given action is. After updating the critic, we move on to the actor. The actor update uses the deterministic policy gradient. Basically, we want to adjust the actor's parameters so that it chooses actions that the critic thinks are better. And the gradient comes from the chain rule. How does the Q value change with respect to the action, and how does the action change with respect to the actor's parameters? And finally, after updating both networks, we softly update the target network. Okay. That means we slowly blend the weights of the target networks toward the current actor and critic, and this slow update helps prevent sudden shifts that could destabilize training. And that's okay. And here's a math. And what is this math behind those updates? Okay. So when we update the critic, the formula for the target is here yi plus and gamma q prime si plus 1 and mu prime si plus 1. That's saying Take the immediate reward and add the discounted value of the next state as estimated by the target networks. The loss for the critic is then the square difference between this target value and what the critic currently predicts for that same state action pair. The actor's gradient is given by this, you can see. And again, this is just a chain rule. How does a Q change with action and how does action change with the actor parameters? And let's move on to exploration. So, since we are using a deterministic policy here, we can't rely on randomness in the policy itself. That means we have to explicitly add noise to the actions to explore the environment. One commonly used method is called Ornstein-Uhlenbeck process. It is useful, especially in control tasks, because the noise it generates is temporally correlated. It doesn't jump around randomly. It moves more smoothly, more like real physical motion. And the formula for the Ornstein-Uhlenbeck looks like this. And this defines how the noise evolves over time. Theta controls how fast it returns to the mean. Mu is the mean itself. And sigma sets how strong the noise is. And WT is a VNR process, basically standard Brownian motion. If that's too much, there are also simpler ways to add noise. And what are they? You could just use Gaussian noise, sample from a normal distribution, and add it to the action. Another option is parameter space noise, where you don't add noise to the action, but the policy parameters. To the policy parameters. And that can help with exploration too. And finally, there's adaptive noise scaling. You start with more noise, then reduce it gradually as the policy improves. So we will take a step back and look at why DPG is used at all. What does it offer? First, it is more efficient in terms of data because we don't have to sample multiple actions from a distribution or integrate over them. We use fewer samples to learn something useful. Second, the gradients are cleaner. The updates we get from DPG have lower variance than what you would get from stochastic methods. That often leads to faster and more stable learning. Third, it is better suited for high dimensional actions. In those cases, sampling efficiently becomes difficult with stochastic policies, but deterministic ones handle it better. At last, DPG is the foundation for more advanced methods. Algorithms like DDPG and TD3 built on this. So, if you understand DPG, you have already got the core idea behind them. And okay. Speaking of that, let's wrap up with a quick overview of where DPG leads us. DDPG stands for Deep Deterministic Policy Gradient. It takes DPG and adds deep neural networks plus a few ideas from the DQN world, like target networks and experience replay. This lets it handle more complex problems with high dimensional states. Then we have TD3 or Twin Delayed DDPG. This is an improvement over DDPG. It fixes some issues like our estimation bias in the critic. And it uses two critics instead of one, delays the policy updates and applies some smoothing to the target policy. These tweaks help a lot with stability. And there is SAC, Soft Actor Critic. Now, this is not deterministic, it is the classic method, but it borrows some structure from deterministic methods and adds a different idea, entropy. It encourages exploration by not just looking for actions with high value, but also trying to stay uncertain for longer. That helps avoid premature convergence. So overall, DPG is the starting point. And if you get these down, it becomes easier to move on to more advanced actor critic methods later. And thank you for listening. That's all for this lesson. See you in the next video.